Up towards at the moment is a proof of the theorem, which is often called the calculus theorem. It's proof by Kirby, and the paper that I'm referencing is Kirby, and it's called a calculus of framed links in S3. I was too lazy to go to the library to get it, and I just Googled and found someone that scanned it. So, it's in Inventiones, but you can find the scanned PDF version somewhere online. It's not in the issues of Inventiones that are online. Okay, so what is the theorem about? So we have one. So I can't really state the theorem until I remind you what. So we proved. So we now know that every closed oriented three manifold M is the boundary of a four manifold X, and where X is simply connected, X is compact, simply connected, and actually the construction, simply connected does not imply this, but actually the construction is that X equals a zero handle union two handles. It is possible to have a simply connected four manifold that requires one handles in its construction, and it's sort of a question whether you can get rid of one handles. But but certainly if it's by our constructors showed that it was a zero handle and two handles, and so therefore it is simply connected. But in terms, if you really only care about three manifolds, the point is this. So this implies, well, we really got this the other way, right? This is equivalent to saying that the three manifold M can be obtained from the three sphere by surgery on a framed link L in S3. So what we said that we showed that there was a sequence of knots inside S3, sequence of embedded circles inside S3, such that, and with framing, such that if you remove the solid torus neighborhood of consecutive circles and move solid tori back in certain ways, given by those framings, you would change S3 into M. Right? What I want to introduce a notation, which is we'll say that, and so the key idea here. So what is a framed link? For those who are brand new, a framed link might be something like a simple example, something like this. These are two knots, and I'm drawing them in R3, but by stereographic projection, S3, I'm thinking of it as R3 meaning infinity, and then I draw two knots that might link, and they might, of course, have knotting, but I'm not going to draw that. And then there's some twisting that goes around, as you want to record some kind of twisting as you go around the knot, and we will record that in S3, which is writing in integers. So I might, for example, write +1, -2, something like that. And that means that these are not just knots, but they also come with some preferred amount of twisting around. And so, for example, the twisting here would be given by one full right-handed twist and going that way. The twisting here would be given by two full left-handed twists and go around. So that's an example of a framed link. And the point is that such a framed link describes two different things. So one thing is so L in S3 describes, first of all, the way we've thought of it is describes a four manifold, which I call X of L, 4 manifold obtained by taking a 4 ball, 4, which is what we're calling a 0 handle here, and then gluing union 2 handles, some number of 2 handles attached along L. Just quickly remind you what that is. So the 2 handle is B2, a disc cross a disc, and when you attach it, you glue attached by an embedding from, so S3 is the boundary B4 attached by an embedding from S1 cross B2 into the boundary B4, and this S1 cross B2 is a thick neighborhood of one of these knots, and this amount of twisting is telling you exactly how, as you go around the S1 direction, how the B2 rotates. Okay, so that's one thing it describes. The other thing it also describes what you might call M sub L, which is the boundary of X sub L, and that's the 3 manifold. Okay, so the frame link describes both the 4 manifold, not all possible 4 manifolds, but it describes some class of 4 manifolds, and then it also describes the 3 manifold boundary. And the question that this calculus is addressing is, suppose 2 framed links describe the same 3 manifold. Are there some moves that you can use to get the one frame link into the other frame link? And so the theorem says that if 3 manifold M sub L1 is diffeomorphic M sub L2. By the way, everything is oriented. This is an oriented 4 manifold. The links actually determine oriented 3 manifolds. This diffeomorphism is orientation preserving. Then the framed link L1 is equivalent to the framed link L2, where this equivalence relation is generated by certain moves. Okay, where equivalence is the following moves. Okay, so there are 2 moves. One of them is what we have already recognized as a handle slide, except calling it a handle slide is really a move on the 4 manifold. So we have, in terms of just a move on a framed link, let's just remember that this is equals the band. I call it a band connect sum, and I'll just remind you by example what that looks like in a second. So you slide one of the links, frame links, over the other frame link, and it changes one of the frame links and not the other. So that's one move you can do, and the other is adding an unknot with framing plus or minus 1, unlinked from everything else, just off by itself somewhere. So you can just put that. If you have your frame link, you have some complicated link, and it's got lots of knottings, and all by itself, way over here, you could add a 1 or a minus 1. And that doesn't claim is. The claim is, first of all, that these 2 moves don't change. Actually, this is an if and only if. I should say this. Okay. The one direction that these 2 moves don't change in 3 manifold is not hard to do. We'll show that first. The other direction that the 2 moves are the only moves you need to get between the 2 links is much harder. Okay. But let me just remind you, make clear what these moves are. So, well, this one's pretty clear, right? You've got your link, you just all by itself, you add to the link a single unknotted unlinked component with either +1 or -1 written next to it.
Would it be fair to say that you start off with L1 and then you either do 1 or 2 to achieve L2, and that's the...
Oh yeah. Repeatedly moves. You repeatedly do any sequence of these 2 moves.
So you add a +1 and then handle slide.
Yeah, you can add a +1 and then you can slide over it, for example. Okay, let me give you maybe just a simple example to demonstrate. Actually, let's do the example right now that demonstrates some of these moves. So, well, we'll start with the empty diagram, right? Which is that. So no link at all, the empty link. And that is, of course, just, if L is just the empty link, then M sub L, L1, M sub L1 is S3, the empty link. Okay? So then we could modify that by doing, these moves are called, this is called blow up. The reason it's called blow up is because if you've done any algebraic geometry, this we'll see later that adding a +1 or -1 corresponds to connect summing with complex projective plane, or adding a +1 is connect summing with a 4 manifold with CV2, or connect summing, if it's a -1, connect summing with CV2 bar, the reversed orientation, and that's exactly what an algebraic geometry is, a blow-up operation. But it's a little bit misleading to call that 3 manifold operation blow-up or a link operation, but it all comes from the same thing. Okay, what about, so let's do move 2, let's do a blow-up, and then we can get to just +1. But how about we do, let's do 3 blow-ups, okay? Well, actually, this would not be the algebraic blow-up because a -1 is the algebraic blow-up. But anyway, let's do a bunch of blow-ups. Let's do this one, another +1, so this will be L2. We're doing 3 of those. Okay, and of course, still we have S3. That's the theorem. I'm not proving it free yet that that is S3. And now I want to do some slides to show you what can happen. So, for example, I can slide. I think the first thing I want to do is I want to do a slide this +1. Yeah, I'm going to slide this -1 over this +1. Okay. I think we might have done an example like this once before. So the slide is, the way I presented it in class is you want to think of, let's draw the framings as parallel push-offs. So this is going to go around here with the framing +1. So, and here we also draw in terms of just figuring out what happens to the knot, if you don't care about the framing, then you take a push off, you just simply do this to the 2 knots, and that gives you your new, that tells you what happens to this component after you slide it over that. But we also want to understand what happens to the framing. And so in order to do that, we should really have a parallel. So that is the handle slide operation if you don't care about framings. Except you need to know the framing of this one in order to know how many twists were here on this one. But in order to understand the framing, you should also, let's try to get -1 farther away. So let's draw the parallel push off of this, which is framed left-hand twist this way and around. And now I should, I need another copy of this, which we're going to over and then back. Okay, so what you should see is that there's actually just a single twisted annulus connecting the white, the green, and the blue. Okay. But now I claim that actually that simplifies. So that was the handle slide here. Okay. And that simplifies stuff like +1. And then I claim that when you clean all that up, you haven't changed this one at all. It's just sitting there claiming +1. But I claim that this guy now sits off here with framing 0. So what you want to think is that the blue, you look for, well, maybe ignore the blue for the moment and just notice that this new component here goes through and then links at +1 once. Now you want to say how many times does the blue twist around this new component, and you observe because it's got a left twist and a right twist, it ends up being 0. So that's the situation there. And I wish that this had been, I wish that this had been -1 all along. So let's make this a minus 1 for a second. First of all, this is an interesting configuration that will be relevant to us later as well. So let's just remember that it's worth remembering that this is sort of equivalent to +1, -1, that little piece in the box there. But now, if suppose this was a -1 as well, then I can do one more step. I'm going to slide. Let me slide this +1 this way. And the same thing will happen. Okay, so I'm going to do another slide here, and the same thing will happen, and that -1 will be unchanged. And if you can imagine, the symmetric operation works just fine. So I'll get this and this, and these will both be frame 0. Okay. And now there's one more slide I want to do, which is I want to take this, finally I want to slide that over that. And when I do that, notice the sliding over a 0 frame thing is easy. I don't have to think really much about frames at all. No frames will change. And this will come around, and it'll just go around the outside. It'll pop off of everything again. You can see that here, so I'm going to slide it over and come up and around back, and then here. And then come unlinked again, but its framing doesn't change. So finally you'll get to -1 and 0, 0. What this means is that in the presence of this sort of loose -1 here, I'm able to change this +1 into a 0. But without that loose -1 there, I'm not able to do that. Now, so this is a calculus, right? In the sense of it's a set of operations that you can do on these funny symbols that describe 3-manifold. And the claim is that all these different links are described in the same 3-manifold, which in this case is X3. But I also want to remember, these are sort of two important moves. This one thing important I want to emphasize, that you can get this configuration by blowing up twice in this way, and you can also get a single unframed. If you like, you could now do the move, I should have said add a, these are all reversible, right? So then you could erase this and get to I think it's an equivalence relation that we're talking about. So. And that's the theorem. And there exists I believe that there are some mistakes in the proof as it's written down in here, which have been sort of corrected in the folklore. And there's also an entirely alternative proof that is like piecewise linear proof using triangulations of 3-manifolds that was by Fenn and Rohr, partly because of those mistakes, and also, but I mean the proof is fixable, and I'll try to present a correct proof using Morse theory and surf theory. I don't know the piecewise linear proof at all.
Is that not? That's because PL's like different in 4 dimensions.
Yeah,
so
but the theorem is only about 3 dimensions. The theorem is, and so the purely 3-dimensional theorem, it can be proved purely 3-dimensionally using piecewise linear 3-dimensional techniques. I'm gonna, but this is the other one. Okay, so. So one of the ingredients of the proof that I do want to prove for you, but not today, is that so I will use the fact that I'm not going to finish the proof of this theorem today. It takes a while. There's a lot of different pieces. The one thing that I'm definitely going to infer is the fact that for any, I mean, I mentioned this last time, I said this differently last time, for any closed oriented 4-manifold, there exists some, I'm going to write it this way, there exists some integers m and n such that if you take x, connected sum with some number, the connect sum of m CP2s, and then you also connect sum onto it, the connect sum of n CP2 bars. So if this just means the connected sum of m and them all connected to each other, and this means the connected sum is bar. I'm using bar for orientation reversing. If I didn't say that earlier, this is the reversed complex projective plane, the reversed orientation. If you connect all these things together, that's a new four manifold, and that is equal to the boundary of some phi manifold for some compact phi manifold. I guess I like this theorem. I like the theorem, but I like its proof even more because it uses 3, 4, and 5 dimensions altogether. So, some compact phi manifold. Okay, so we're going to use all those ingredients. We will use that, and I'll try to prove it later. Okay, so we're given so the proof. This. Given 2. So we get. I'm just going to call it M, which is ML1, and I'm just going to say equals ML2. I'm being sloppy here, they're really diffeomorphic, but I'm just thinking of them as the same, right? In the sense I fix the diffeomorphism between them, or I fix diffeomorphisms between them and some other standard 3 manifold, however you want to do it. And we also get, we get these 4 manifolds, XL1 and XL2. Now, I never said that these 4 manifolds are diffeomorphic. It's just that's sort of the heart of the problem, is to get the 4 manifold. Well, there's 2 parts to this thing. Part 1 is to modify L1 and L2 so that the 4 manifold is diffeomorphic. And then part 2 is to, once I get the 4 manifolds diffeomorphic, it still may have different links. And I want to change one link to another without changing the 4 manifold using these moves. So step 1 is going to be use these moves to make XL1 diffeomorphic. So the way we're going to do this, well, they're not initially diffeomorphic. So I'm going to let I make a new 4 manifold X. These are XL1 and XL2 are manifolds with boundary, right? And so they have the same boundary, and I'm going to glue them together along their boundary. Okay? I'm going to be a little bit careful about how I glue them together along their boundary. So I'm going to let this be. I really wish I had called them 0 and 1. So let me just call them 0, just for convenience, because I'm going to use a cobordism from 0 to 1 at some point. So let me just change that up right around here. It's, I don't know, I'll change it up there, but okay. So let's let x equal XL0 union 0, 1 cross M union XL1 bars. That's a reverse oriented version. So here's a picture of what I'm doing. I'm taking well, actually, let's. I mean, the schematic. The first schematic is here's XL0, and here's its boundary M, and here's XL1, and here's its boundary M. And first of all, when you glue things together, you should glue with an orientation reversing diffeomorphism, but these have the same orientation. So I should reverse the orientation of this whole thing, and then I'm going to produce. The first pass at gluing them together would just be glue them together like this, XL0 and minus XL1, right? Because you're turning it upside down to glue. But actually, I don't want to do that. I want to explicitly remember a collar neighborhood in between, right? So this is going to be 0, 1.
So minus XL1 bar.
Oh, your minus is it's a negative. Okay. So that's just, this is an operation, I mean, this is standard operation. 2 things with the same boundary, you glue them together, but I'm just emphasizing, you're not really going to have to dwell on this, but I'm emphasizing that actually, naturally, when you really do this, so that you should really reverse the orientation of one. But now I want to think about this thing I've constructed sort of differently. I don't want to think of it drawn that way. I want to think of it as, well, actually, let me just emphasize that this now. Well, okay, we would, what we're going to do is try and find a 5 manifold. This is now a closed form. We don't know that it bounds a 5 manifold yet, so we're going to have to modify it to make it bound a 5 manifold. But that's precisely so what we're going to do is, but we can modify. Well, we know that after connect summing, twos, two bars, X will be the boundary requirement. So the point is, I can actually do, so I want to now sort of glue in some CP2s and CP2 bars. Right? Now I can do it, it doesn't matter, I can do it in here or in here. But the first claim is that doing it in here is actually, so the claim is that X, the first claim is that X connects some CP2, or CP2 bar, I'll just do it for CP2, is diffeomorphic to X. Now here's a new symbol that you may not have seen. Boundary connects some, sorry, I want XL0. CP2 minus a ball. So this symbol, this natural symbol, this is I think it's a standard symbol for a boundary connected sum. Boundary connect sum means you remove a ball in the boundary, because these are now manifolds with boundary. This is a manifold with boundary. So what this is saying is you take a 4-dimensional ball from the interior of X, L0, and a 4-dimensional ball out of the interior of CP2. You get 3 sphere boundary components, you glue them together. This boundary connect sum operation says you look at the boundary, you take a 3-dimensional ball, you don't remove it, you just identify a 3-dimensional ball in the boundary this, and you identify a 3-dimensional ball in the boundary this, and then you put the 2, glue them together. Which is actually, this is exactly the same thing as just saying attach a 1 handle that connects one to the other. That's all that is. The reason that, so in general, connected sum is not the same as boundary connected sum after removing the ball. But I mean, sorry. If this was a manifold with boundary, then you know, in other words, to take 2 manifolds with boundary, connect summing versus boundary connect summing is in general different. But if I take a manifold with boundary and a closed manifold, and I remove a ball from this, then I glue them together. That's the same thing as a boundary connect sum, and maybe that's best illustrated with an example. Right? As I claim, this actually works in arbitrary dimensions, and I won't. So let me just do a 2-dimensional example to illustrate this. So suppose that this looks like genus 1 surface with boundary. And suppose that this is another closed genus 1 surface, right? So the connect sum of the 2 of them is going to be, I'm going to remove a disk here, remove a disk here, and smush them on. I mean, you may be suspicious of this argument, but let me remove the disk kind of close to the boundary, right? So then this is going to be, and I think this is going to give you this little bit of genus sort of sticking on the side there, right? That's a picture of what it would be to remove this disk, glue it in there. Now the boundary connect sum, that's the picture for the connected sum. The picture for the boundary connected sum picture for boundary connected sum here would be, I'm not doing anything different here, but now I'm supposed to take this thing and remove a disk first. So I remove the disk and it's going to look like this. So those are my two pieces. This is representing my CP2 minus the ball, and this is representing my XL0. And then I'm supposed to just put a little handle over them, over one to the other. The point really is that this disk where I glue them together, I can just make it closer and closer to the boundary, and then this is essentially just happening right at the boundary. So maybe the best way to prove this is to do it in a half disk near the boundary. So you can write, such a proof is actually written down carefully in full generality in dump descriptions again. So let's see dump descriptions. So I'm not going to say anymore, but my claim is that that two-dimensional picture is not just a cheat that works because you have a classification of surfaces, but it actually really illustrates the full phenomenon. And so now what I want to do then is that say, so we talked about it briefly before, but a link diagram for CP2 minus a ball is, so this equals before two handle, where the two handle is glued along just a unknown frame plus one. And I'm just doing CP2. And if I do CP2 bar, it's going to be a minus one. And so then the final thing is that if I want to do a boundary connect sum of two four manifolds, each given by a certain link, then that corresponds to just putting the two links side by side. Because, so the final thing is that, this is a link describing this four manifold boundary. This is a link describing that four manifold boundary. I can think of those two links as being two disjoint S3s, which I connect by a one handle. But then connecting that one handle is just like putting, we already seen it as putting a wormhole between them. You put a wormhole between two S3s and they just become one S3, and the two links are just side by side there. Okay. So therefore, this connect summing with CP2 is precisely one of our moves. So the point is now I can, so therefore, using our moves, we can assume, we can do those moves to either L0 or L1, it doesn't matter, and we can assume that this X is really equal to the boundary of the 5 manifold. And so in this 5 manifold now I want to try to use this 5 manifold to show how to, I want to use this 5 manifold to show how to modify these links, L0 and L1, so as to make the 4 manifolds different. And now here's the schematic for what we're going to do. So I want to draw this picture differently. I want to draw that picture somehow like, something like that. Now, so the idea is that this is going to be XL0, this is going to be XL1, and this is the product 0 and 1. This is the interval 0, 1 cross M. So this over here is M. I'm just sort of taking that thing and folding it right angles. Because I want, and now here's the 5 manifold that the 5 manifold that bounds somehow in here. So this is Y5. This is just an entirely schematic picture, but it means something. What I really want to do is say that I'm thinking of Y5 as the 5 manifold Y as a cobordism from XL0 to XL1. It's one of those kind of cobordisms we saw where I have on the side, this is a cobordism with corners, if you haven't before. So Y is a cobordism from XL0 to 1. And I'm going to put on it a Morse function. So choose Morse function f from y to 0, 1. So respecting this coordinate structure, this cobordism structure. So the idea is now I have this schematic picture of this 5 manifold, and that's mapping to interval 0 to 1. So what respecting the cobordism structure means that it sends XL0, that part of the boundary, to 0. It sends XL1 to 1. And on this product side, it's this is 0, 1 cross n mapping to 0, 1 by the standard projection of the first factor. Okay? And then it's got critical points in the interior. Okay? So, I mean, that's something else for me to think about, that you would never, if this is, we just construct the map so it doesn't have any critical points on the boundary. So it has critical points in the interior. And okay, so for those of you who are just visiting and just getting an impression, a picture of what's going on, a Morse function, if you've never seen one before, is a the most if you have a function from a smooth manifold to the reals or to interval 0, 1, it's just a generic function. It's sort of generically what they're going to look like. And the important thing is to understand what happens at critical points, the places where the derivative is 0. And at those points, you want some non-degeneracy behavior, which corresponds to very higher dimensional versions of minima, maxima, and saddles. You don't want cubic type critical points and so on. So this sort of typical picture of a surface, I have a minimum, which is an index 0 critical point, a saddle, which is an index 1 critical point, and another saddle here, which is an index 1 critical point. And here I don't have any maximum. In this one, I would have a maximum if I just take the height function. I would have a maximum, which is an index 2. So the index refers to the number of dimensions that go down. So here there are no dimensions going down. Here there's one dimension going down, one dimension going down. And here there's 2 dimensions going down. So anyway, we'll get these critical points in here. And the critical points give a decomposition of the manifold into what are called handles. And that's so that's our goal is to try and understand this 5 manifold, and want to understand how, as we go from this 4 manifold here up to this 4 manifold here, how the 4 manifolds change. And so slices are going to change, just as in this case, levels. The point is we're going to see 4 manifolds, lots of 4 manifolds moving across here as level sets of this function. Just as here you see 1 manifolds, circles, moving as level sets. Eventually 1 circle becomes 2 circles. Something's going to happen here. These 4-dimensional slices are going to change their topologies, and we want to understand it. And actually, the way we're going to see that both of these, we're going to find, what we're going to do is consider a 4 manifold, quote unquote, in the middle, which is going to be we're going to see how to modify XL0 so that we get a 4 manifold in the middle, how to modify L1 to get the 4 manifold in the middle, and see that those are in our list of allowable movements. The first step, though, is going to be, we already know from stuff we've done before that we know that we can assume F has no critical points of index 0 or 5, so no minimum or maximum. What are the possible indices? 0, 1, 2, 3, 4, 5, okay? And 5. And we're going to get rid of 0 and 5, and we're left with 1, 2, 3, or 4. The next thing we're going to want to do is get rid of 1s and 4s. So, next. If I can get rid of 1s, I turn it upside down and use the same argument to get rid of 4s, okay? Because upside down and 4 is 1. And so I want to show how to get rid of 1. I'm actually going to change the 5 manifold. The 5 manifold may essentially need, this particular 5 manifold may require index 1 critical points, right? but I'm going to modify the 5. Anytime I see an index 1 critical point, I'm going to actually trade it for an index 3 critical point. That's the trick. So I'm going to trade index 1s for 3s at the expense of changing the 5 manifold, but not changing the 2 endpoints, of course. And once we get, I'll show you how to do that in a minute. Once we do that, then the same argument will trade 4s for 2s, because flip everything upside down. And then we'll eventually get to just 2s and 3s. So then I'll be able to order them so the 2s are below some level and the 3s are above some level. And then we're going to take this middle slice, and we're going to show how when you cross a 2, you do one of our moves.
Just like the Hagar split.
It's just like the Hagar split. But it's going to be exactly. But the first thing is to clean this up and get rid of the little ones. So what we want to do is consider us. So first of all, we can always, let's assume the ones are all. We can remember we can lower. We can always order the critical points by index, right? So we can lower the ones below everything first. So this is how we do this. Okay, how to trade ones for threes. We lower the ones below everything else. And now I'm going to focus on a slice, a slab, going from XL0 up to something where I just have a single index 1 critical point. So consider, I guess I could say, F inverse of 0 to epsilon, for some epsilon, such that containing exactly 1 index 1 critical point. So this thing, so F inverse of 0 epsilon is equal to, if we morph it to XL0 cross, an interval, cross 0 epsilon, union a 5-dimensional 1 handle. 5-dimensional 1 handle means B1 cross B4, and it's glued to the top end of this via a map from, so we do via embedding S0 cross B3, B4 into XL0 cross epsilon. So we've got this 4-manifold cross an interval. In the top, we're just attaching a 1 handle, so we've got 2 4-dimensional balls inside that top 4-manifold. We're going to glue something that goes from one to the other, so it's going to attach this B1. It's just an interval. Interval across 4 balls, and that's this operation. So the question is now, how does that change? Let's understand how that changes the new boundary. So the boundary then of F inverse of 0 epsilon, of course, it has 2 parts. It's the bottom boundary is XL0, actually minus XL0. Disjoint union, union, because I got the side. But the top part is, I'm just write this, the top of F inverse of 0 epsilon. Well, what have you done when you attached S0 cross B3? Maybe it's important to emphasize that everything was connected. So when I'm attaching a 1 handle, actually this works in any dimension. When you attach a 1 handle to a connected boundary, since the feet of the 1 handle can be connected by an arc, you're really creating a loop, new loop, right? And actually all you're doing, so if you just do the 3-dimensional analog of this, so suppose I had something 3-dimensional on a solid 3-dimensional thing, and I attached a 3-dimensional 1 handle at 2 points. By completing those 2 points to an arc, and then sort of imagining thickening that arc a little bit down into the 3-manifold, you discover that all you're doing is doing a connected sum with S1 thickened up. Okay? So the point is, this is just XL0 connect, the way the, sorry, and then the way the boundary changes the boundary changes by connect summing with the boundary of this, which is S1 across this sphere, whatever dimension is appropriate. So the boundary changes by, in this case, it's S1 cross S3. So we've changed XL0 by connect summing with S1 cross S3. It's hard to keep the dimensions straight, I know, but at least to remember that this is a four manifold, so we better not connect sum with some 5 dimensions. This connect sum is happening, even though XL0 has boundary, this is happening away from the boundary. That's the other thing to remember. This is extra tricky because we've got boundary off here on the side of XL0, but we're adding a handle here. Right? So we had the handle in there, and then above it, you get something which is diffeomorphic to. We just took this thing and connected some with S1 plus S3.
But the links have to live in the boundary.
The things we're attaching along.
With these surgery links. Like where
Those surgery links, the L0 and L1?
Yeah.
Those
have to
actually,
be,
where did those live? Okay.
those have to live on the side.
Actually, no. XL0, if you think about it this way, it's built out of a, so that's a four manifold built out of a 4-ball, and then you attach links to it, right? The links are in the boundary of that 4-ball. That 4-ball is sort of back here somewhere. Because this is the result, you want to think about on XL0, the original picture is, it's a 4-ball and then you attach handles, so the link lives in the boundary of the 4-ball. Now I take that thing and turn it on its side, the boundary up here, the 4-ball, the original 0 hemisphere. Okay. Now, what I'm going to do is I'm going to replace F inverse of 0 epsilon by some other 5 manifold, which also has two boundary components, XL0 and XL0 and XL plus S3. So I'm going to create a new, and then I'm just moving that in. That new 5 manifold will be constructed by attaching a 3 handle rather than 1. So the claim is that you could do, so maybe this is an appropriate exercise. This will be exercise. Show that, actually the best exercise to do is show that if you attach let's see if I can say this right, I won't do, there's an arbitrary dimensional version of this, but I won't try to write this down. If you attach a 3 handle to XL0 across 0 epsilon, this is a 5-dimensional 3 handle. Well, and I have to be careful now about what I want to attach it along. So I'm going to attach it along. 3 handle should be attached along and S2. Okay? So 3 handle means B3 cross B2. And you attach it along and S2 in XL0 across epsilon. Now in this case, there are lots of different spheres you could possibly, 4 manifolds in general have all kinds of interesting and different complicated spheres in them, but I want it to be one which bounds an embedded 3-dimensional ball in XL0 cross epsilon. Then the top, the new, then you get a cobordism from XL0 to the same thing, XL0 connected sum S1 cross S3. So what's the basic idea? The basic idea is that I've taken basically you just have to understand what the surgery does, right? And the surgery is going to replace I'm gonna take out a neighborhood of this S2, which is S2 cross B2, I'm gonna take it out, and now I have an S2 cross S1 boundary component, and I'm gonna fill it in by B3 cross S1. Okay, that's where this S1 direction is gonna come from, is this cross S1. Where this S3 direction is gonna come from is the fact that I had a B3 that this S2 bounded, and then I've got a B3 from inside the handle, and those two B3s are going to fit together to make an S3. So that's, we should stop. But once you believe that, then you can replace you can replace F inverse of 0 epsilon with a slab like this, which then has a 3 handle rather than a 1 handle. You can trade all your 1 handles for 3 handles and do the same thing on the top, and then we'll see you next time.